I am Professor M.V. Department of Physics, Government First Grade Women's College, Jamkandi. Today we have to discuss BSc 5th Sem Physics 5.1 paper, that is second chapter, Atom Model, session number 13, expression for frequency and wave number of emitted spectral line. Observe here, in the previous class you know energy of the electron in the nth orbit. Now we have to derive an expression for frequency and wave number of emitted spectral line. If an electron jumps from an outer orbit n2 to n2 of higher energy En2 to an inner orbit n1 of lower energy En1, the frequency of emitted radiation is given by E equal to energy of the electron in the higher orbit En2 minus energy of the electron in the lower orbit En1. Now the difference in energy is emitted in the form of electromagnetic radiation having frequency nu, therefore we have to equate it to h nu. Therefore nu equals to En2 minus En1 by h. Take it as equation 1. We know in the previous expression, in the previous class, energy of the electron in the nth orbit En equals to. Now on the same basis we have to write energy of the electron in the lower orbit En1 equals to minus m e to the power 4 z square divided by 8 epsilon naught square n1 square h square, and energy of the electron in the higher orbit En2 equals to minus m e to the power 4 z square 8 epsilon naught square n2 square h square. Now substituting the values of En1 and En2 in equation 1, now equation 1 becomes nu equals to 1 by h. Substitute the value of En2 minus plus substitute the value of En1. Now take the common factor outside. We get frequency nu equals to m e to the power 4 z square 8 epsilon naught square h cube. Now inside the bracket we get 1 by n1 square minus 1 by n2 square. For hydrogen z equals to 1. Therefore frequency nu equals to m into e to the power 4 8 epsilon naught square h cube into bracket 1 by n1 square minus 1 by n2 square. Now we have to define wave number. The number of waves contained in a unit length is called wave number. It is denoted by nu bar. Therefore wave number nu bar equals to 1 by lambda. Therefore nu bar equals to 1 by lambda equals to nu by c. Frequency into wavelength equal to velocity of electromagnetic radiation, that is nu lambda equals to c. Therefore nu bar equals to, substituting the value of frequency in the above expression, we get wave number nu bar equals to m e to the power 4 z square 8 epsilon naught square h cube c into bracket 1 by n1 square minus 1 by n2 square. For hydrogen z equals to 1. Therefore nu bar equals to m e to the power 4 8 epsilon naught square h cube c into bracket 1 by n1 square minus 1 by n2 square. M mass of the electron, E charge on the electron, epsilon naught permittivity for free space, H Planck's constant, C velocity of electromagnetic radiation, all are constant. Therefore the entire term is constant. We have to denote it by capital R. Inside the bracket 1 by n1 square minus 1 by n2 square, where capital R equals to m into e to the power 4 8 epsilon naught square h cube c, known as Rydberg constant. All are constants. Substituting the values of all those constants and simplifying, we get the value of Rydberg constant as 1.097 into 10 to the power 7 per meter. Now we know about the wave number of emitted spectral line. Now we have to study the spectrum of hydrogen. Hydrogen atom has a single electron which is in the ground state. Its spectrum consists of 5 series of spectral lines. The first series, Lyman series. Lyman series consists of spectral lines corresponding to the transition of an electron from higher orbits to the first orbit, that is n1 equals to 1, n2 equals to 2, 3, 4 up to infinity. The value of n1 depends on name of the series. For Lyman series, n1 equals to 1. For first member, n2 equals to 2. For second member, n2 equals to 3. For last member, n2 equals to infinity. Lyman series lies in the ultraviolet region of the electromagnetic spectrum. Now we go to the second series, that is Balmer series. Balmer series consists of spectral lines corresponding to the transition of an electron from higher orbits to second orbit, that is lower orbit number n1 equals to 2, higher orbit numbers 3, 4, 5 up to infinity. Balmer series lies in the visible region of the electromagnetic spectrum. The first line of Balmer series is called H alpha line. The second line is called H beta line. Third line is called H gamma line. Fourth line H delta line. Already told you the value of n1 depends on name of the series. Therefore, for Balmer series n1 equals to 2, for first member n2 equals to 3, which is known as H alpha line. For second member n2 equals to 4, which is known as H beta line. For third member n2 equals to 5, which is known as H gamma line. Now H alpha line, H beta line, H gamma line, they are the members of Balmer series which are in the visible region. Now we go to the next series, that is Paschen series. Paschen series consists of spectral lines corresponding to the transition of electron from higher orbits to the third orbit, that is lower orbit number n1 equals to 3, higher orbit number n2 equals to 4, 5, 6, last one infinity. For Paschen series, n1 equal to 3 fixed. For first member 4, n2 4. For second member n2 5. For third member n2 6. For last member n2 equals to infinity. Paschen series lies in the near infrared region. Now we go to the fourth series, that is bracket series. It consists of spectral lines corresponding to the transition of an electron from higher orbits to the fourth orbit. Here the lower orbit number n1 equal to 4, higher orbits number n2, 5, 6, 7 up to infinity. For bracket series, n1 equal to 4 fixed. For first member n2 equals to 5, for second member n2 equals to 6, for third member n2 equals to 7, for last member n2 equals to infinity. Bracket series lies in the middle infrared region. Now we go to the last series, that is 5th series. It consists of spectral lines corresponding to the transition of an electron from higher orbits to the fifth orbit. Here the lower orbit number n1 equal to 5, higher orbit number n2 more than 5, that is 6, 7, 8 up to infinity. For 5th series, n1 equal to 5 fixed. For first member n2 equals to 6, for second member n2 equals to 7, for last member n2 equals to infinity. 5th series lies in the far infrared region. You must remember the most important point. In all the series, the first member corresponds to the longest wavelength of the series, and the last member, that is n2 equals to infinity, corresponds to the shortest wavelength of the series. The last member is also called series limit. Now observe here energy level diagram of hydrogen atom. The total energy of the electron in the nth orbit of hydrogen atom is En equals to, you know in the previous class, energy of the electron in the nth orbit, that expression all are constants except n. After substituting all those constants and converting finally in terms of electron volt, the energy of the electron in the nth orbit of hydrogen atom is given by minus 13.6 divided by n square electron volt. For first orbit, n1 equals to 1. Therefore, energy of the electron in the first orbit is minus 13.6 electron volt. For second orbit, E2 equals to minus 13.6 divided by 2 square, that is minus 13.6 by 4, minus 3.4 electron volt. E3 equals to minus 13.6 divided by 3 square, that is minus 1.51 electron volt. For fourth orbit, the energy of the electron is minus 0.85 electron volt. For fifth orbit, the energy of the electron minus 0.54 electron volt. And in the sixth orbit, minus 0.377 electron volt. In the infinity orbit, the energy is 0. Observe here the energy level diagram of hydrogen atom. n equals to 1, n equals to 2, n equals to 3, up to infinity. Horizontal lines represents discrete energy levels. Vertical lines represent electron transitions between different levels. The lowest energy level E1 is called the normal energy state or ground state of the atom. The higher energy levels E2, E3, E4 are called excited states. As n increases, energy of the electron increases. Therefore, the energy levels are crowded close together as we go upwards. In the energy level diagram, the discrete levels are represented by horizontal lines, and the electron jumps between these states are represented by vertical lines. The diagram shows schematically the spectral lines related to atomic energy levels. Observe here Lyman series ends in first orbit. For first member n2 equals to for first member n1 n equals to 2. For higher orbit number 2, lower orbit number 1, which gives the longest wavelength of the series, and n equal to 3. If an electron jumps from third level to first level, we get the second member of Lyman series. Similarly, Balmer series ends in second orbit. The first member starts from third orbit. The second member starts from fourth orbit. The third member starts from fifth orbit. Now, when an electron jumps from third orbit to second orbit, we get the longest wavelength of Balmer series, that is the H alpha line. Similarly, when an electron jumps from fourth orbit to second orbit, we get the second member of Balmer series, that is H beta line. Now, from n equals to infinity to n equals to 2 gives you the series limit of Balmer series. Similarly, in case of Paschen series and bracket series and 5SPHAMV series. You must remember the most important point: Lyman series ends in first orbit, Balmer series ends in second orbit, Paschen series ends in third orbit, bracket series ends in fourth orbit, 5SPHAMV series ends in fifth orbit. Lyman series lies in the ultraviolet region, Balmer series lies in the visible region, Paschen series lies in the near infrared region, bracket series lies in the middle infrared region, 5 series lies in the far infrared region. This is all about the spectral series of hydrogen atom. Thank you to one and all.